Thank you for inviting me and to give a talk about this subject. It's still ongoing, but no problem. It's I will present several topics. I hope I will have time, otherwise I will a bit speed up to the conclusion. But the idea is to look at what we can do for large mass movement and for assessing hazard. And this topic is not solved yet, and then that's why I will present things that are the ongoing work and not really a finished method that in any case, if it will be applied to Taiwan case, must be in any case adapted. So I will start with the summary. We will look at this hazard assessment of large slope movement and the detection of potential catastrophic failure, because you know that there are landslides that are moving but slowly, and sometimes they are reactivated to create disaster and catastrophic displacement. After, I will just show you some simple method to calculate the surface of failure, which is important to deduce the volume, and insist on the conceptual models that are needed to understand landslide. And after giving some example, and an example of cascade effect, if I have time, that occurred in Switzerland recently. Okay, the context is, what we need to do is, if you have what is the hazard level of a large rock instability? We need the identifying criterion and also a simple rule to differentiate if we want to address the problem for a lot of different instability. I heard that here in Taiwan now there are 9,000 large slope instability. Then we first have to differentiate between this case, where you start with a small movement and then it's like a dormant landslide, or this one. Then you have several cases in between, but I mean that you need to differentiate it, which slope will fail catastrophically. Because these two are similar landslide, but at the end one can fail more in a more rapid way. Then we need to identify instability, rating the hazard, and then assessing the volume, because the volume is important for the propagation distance, and also to assess, especially here, the susceptibility to solicitations such as earthquake or typhoon. And after that, there is one thing which is important, and very important, especially here, and you know that after earthquake, like Chichi earthquake, you have a lot of delivery of sediment, and you have disasters that are linked to large landslide that occurred, which is the cascade effects. How to deal with such scenario with multiple step event. Then there is a consequence for hazard. And if at the end, I will try to show you this Bondo example that occurred last year in Switzerland. So, starting with mapping, if you look at this image from Professor Chigira, who worked on the Talas typhoon, here you have the slope image of the Akatani landslide of several million cubic meter, and you can see here that he was able to find the scar before, and this is the LiDAR image after. And you see clearly that this was the limit here of that was identifiable before the landslide. And then after that, what you need to do is to understand why it can move down in a catastrophic way. On the opposite side, there are some recent study in Italy, and the Italian colleague must know this study, that they are showing now that there are small movement of large instability during a co-seismic movement near, for instance, L'Aquila earthquake, 6.3 magnitude earthquake. Then it moved by a few centimeters, a large landslide, and the model they propose is fitting more or less well the result. This is one thing. And the next, another place with the, you remember that there were three earthquakes during the last year in the central Italy, and another earthquake triggered also a movement in the slope. But in that case, it seems, after the early work that have been done, that using some bit more sophisticated Neumark model, they showed that in that case it was mixed between movement due to seismic movement and tectonic movement and slope movement. This is ongoing work. I cannot tell you the exact, if it's right or not, but you see that now we can start with the INSAR data, because I forget to tell you that it is satellite image, that the satellite data from which you can extract the movement. So this shows you that landslide is a complex phenomenon that evolved as its own life up to catastrophic failure if it occurs or not. But you see that in any case the slopes are going down. Why the idea to create an assessment of large slope hazard comes from this Kilchenstock in Switzerland, where no catastrophic disaster occurred, catastrophic failure occurred. In 1932, Heim, a famous geologist for landslide, look at this instability. You have the village here, and this is the instability here. And he was afraid that this was failing on the village. And this is the movement. You see, this is 4 meters. The movement that they measure during this period in 1930, in the 30s, and he evacuated 2 times the village. But at the end, this, as you can see, it's Google image, it's a recent one, it's still there. Then you see that this is a very fast moving instability, but at the end it's still there. Then you have to differentiate between all of these. Then how to go to hazard susceptibility. The crude and advanced, the traditional classification do not include clearly the deformation quantification. It gives you the type of movement, but not the deformation state. Then here what we will do is to consider the present and past activity of the landslide. And also looking at the rockfall or the displacement. And also we need to quantify where it's located and the volume it is involving. And for sure the mechanism is necessary. If we don't have this evidence, in that method we don't consider, we don't address the problem if we don't have one or two, the condition 1 or 2. So ideally, to quantify hazard of massive rock instability, of large landslide, we need to have a lot of information, such as the mapping, the volume, the unstable volume, the structures, the rock mass quality, the failure mechanism, the groundwater condition, and so on, which is a lot of things. But it's not easy to address that if you don't have a lot of money. So then we can start with a very simple thing, saying that we can look at the deformation of the slope, and in a very simple way, which is not the true strain, but it's a global strain. It's very similar to what has defined Professor Chigira, and it's the length of the original place of the landslide and the ratio between the displacement, the total displacement that you can measure here or here, and the difference between the length at the full length of the landslide from the scar to the toe over minus the length of the original body divided by the length of the original body. Then you have a deformation, a strain, a global strain, and then you will have time and the deformation path. So starting from that, this gives you a sort of activity and And so you can deduce velocity or strain rate from that, but also the state of deformation. This gives you the state of deformation, and computing that with time, you can get the strain rate. So, also starting with this, then, as you have seen with Kirchenstock, you have different solutions, that you have different type of instability. For instance, Kirchenstock, it's probably this case, where you have blocks that move fast, but dismantle completely. Then, rising water pressure in that case is very difficult. So, the quantification we propose here is also to see where is located the deformation. Is it at the top, at the toe, and what is the amount of deformation at the top and the toe? For instance, you have this case, which you will not see any movement at the toe, but a lot of movement at the top. You have seen many videos shows you that large rockfall or rock slide initiate at the top. And it's very strange, but it's like this. But it's also because the strain is the larger, or the displacement is the larger at the top often. And then you can quantify this. And then I will not enter in detail, but you can make some type of landslide and saying that this is one of the worst case scenario with this one, because this is like a bomb. This is, you just start and you think it's okay, but it's very bad in the top. And this means that there is a lot of deformation. And this maybe is less sensitive. So, from that, you can also now look at the strain velocity, which is just given by this formula. I will not enter, it's very simple, but the strain velocity, the strain rate, sorry, will give you an idea of the evolution of the activity of your landslide. Okay? This is important because if it's fast, the deformation is fast, it's not good in a way. And also, what is interesting is that it's not scale dependent. You know, because if you have a displacement of 10 centimeters over 1 kilometer, that's not a lot. But if you have 10 centimeters over 10 meters, this is a lot. Then that's why it's useful. So, the state of activity can be then demonstrated by either the strain, the strain rate, or by evidence like rockfall or recent movement deformation. And also what you have to look at is the reaction to external input like heavy rainfall, earthquake, and so on. Then you need to have a sort of sensitivity. The next thing you have to address is where you look at on the field, where you can see the activity. It can be rockfall, for instance, we took this example because in the Alps is like this. Then you can have a rockfall at the base, which means that the stress is there, or on all the slope here, and then it means that the full slope is starting to be stressed. This is also an important aspect. And then summarizing all these, take my time. If you summarize all these, then you can try to do a sort of a chart where you have activity deformation chart. And this chart, you can recognize the different type. And here we classify this. You see there is the 1, 2, 1, 1. It means that this is the deformation, the movement at the top and at the toe. And if you have 1, 2, it means that it is extension, because there is more movement at the toe. And so, here you classify, all these cases are worse in that direction. And here you have the activity. If the activity, there is no activity, then we consider, it means that you have almost no movement, even past movement. Because if you have a scar, then you go up straight. So, on one side, you have the strain rate. I gave some numbers that can be changed, which is, you see, 0.01% per year. And you have a second parameter, which is the rockfall, the activity. And you have two lines. Usually, if you have only one of these parameter evidence, you will be on that line. Or if you have the two, then you go on the upper line. So this is, and if you are here, and there are some, because of the strain rate, and then there is activity, you will move up, okay? Because you see some rockfall activity or deformation on the field. Now I will go back here to show you later some example. But now I just want to show you one method to deduce volume in a quick way, the volume of deep-seated landslide. So the idea is to use the sloping local base level. The thing is, when you have a spur like this, what you can do is to make a straight line saying this material can be the first that you can erode. And then numerically it's rather easy to do that. And you can you use a DM, and then you do the average of your neighboring point in altitude in your DM, and if your altitude of the DM is higher, you replace by the average. And you do that iteratively, and you will reach this. And if you add a tolerance, you will get a quadratic surface of our line, and then you can curve it. So here it doesn't work, my animation. It's a gift, but normally you will see how it comes from here to there. And this is simply the way when you have the average of this lower than this, then you replace it, and so on. So the result is, for instance, if you have a river network, you will have the line like this, and then all this material is the erodible material in this slope, which is, it's because the concept of local base level usually is on a flat area, it's a river, a lake, the sea. But in that case, it's the sloping local base level. So also why it's more or less relevant to use a quadratic surface. If you check here, is for instance a simulation by Flack, and if you you fit a curve, then you see that you have a very good fitting with parabola. Then you can make additional. You can do additional condition. It can be like this, straight, curved, or you say I don't want to dig below the surface here. Then you fix 0, or you put a minimal slope. So this is an example again on Akatani landslide. We worked with Professor Chigira, and here you see the result. I did the test blinded. It means that I received the DM before, here's the DM after, but the DM before, and I draw this first, and then I draw this one, because I knew that it was wrong, and then this is the one that you can deduce by the DM before and after. So, this is an example, and you see that at the top where there is no deposit, that the model are following rather well the topographic line. So you can do the opposite, and here is the case when you rebuild the former topography using the inverse, and you see that this is following more or less the topography here by using the DM after and rebuilding the topography. And this is now, because you have a sort of model of your failure surface, then you can calculate your volume, because you have the failure surface below the deposit. Here is the example of the thickness above the failure surface. So this is the cross-section. You see the longitudinal cross-section. This is the topography after, and in fact, this one has some deposit up to 10 meters, even a bit more here, just after. And then you see this is the model. You see, this is very close to what is observed, and this is the section here, transversal section, which is rather good. There are also fault that controlling here. Even with fault, it's rather good, and this one is too large. You see, and so there is another cross section here. So this, you see that it's very simple. You can do it in 5 minutes. And you can get this surface. And then you can deduce volume and so on. Then why also, I will just stress the problem of conceptual model. the conceptual model is really important, because I will not enter too much in detail, but conceptual model on slope is very important, because first, you don't know really, the models, the numerical model, are not able to capture everything. And often, it's not possible to capture all the phenomena. Then for propagation or for stability, you always need to tune, and you cannot model completely a catastrophic landslide. So, and it's also important because conceptual model normally is used to be updated every time you have new information. And the conceptual model also is really important if you want to implement a monitoring system, because you will get where are the best position to put your GPS, for instance. So, conceptual model is simply here, it's inspired from work from Aliardi et al. You see that often you have deep-seated gravitational slope deformation that are affecting the whole slope, and inside you have more active landslide. And often this is the dangerous one. The large ones are often are moving, but not necessarily giving catastrophic disaster. This is I think you will have more information by Federico later. So now we need to define the zones that are unstable. But when you define that, you need also to define your landslide. But it's really important to define the environment, especially for the triggering factors, and also to understand the system of landslide. Okay, this is really fundamental. And where it stops. Now, where start a landslide and when it ends? Gravity movement can start, on the slope, but maybe it takes two valleys inside. It's possible, because you have also the tectonic extension and so on. And the greatest one can be the landslide that goes from the mountain belt to the out part of the mountain belt and going to Moho. And you know that there are some Himalaya is collapsing. It's exactly the same. But this is just a bit provocative. Now, what you need to do when ideally, you need to refine your model. If you have, what you need to do is where are the formation, where are the activity? Then at first you will not have so much information. And then you need to improve it. And with time you need to go to more detail. It means higher resolution. And then you can start to understand fully your instability. But this is an iterative process. And you can see here that you start from observation, you create a conceptual model, and then you can implement monitoring, evolution, you look at the evolution of landslide, and so on. And on the other side, you have mathematical model, and you can compare to mathematical model or computer model, and then to check if everything is working and if you understand well. And then you have your landslide state. And after you have to update, because a landslide has an evolution. So, the seconds you can, for a conceptual model, will be here. First, you will map it. Second, you can look at the displacement if you are able by INSAR or also any data. And then you will do a cross-section, because you need to have the third dimension. And so, now you need to look at the failure surface. Where is the failure surface? Deduce from that or from different models. And the last thing is really, if you have borehole, then you can also deduce the behavior, the mechanisms that are affecting the mass. Where are the different types of rheology? Because a landslide is not only one rheology. And then the behavior map. I mean that some place will be rockfall, some place will be flow, some place will be sliding surface. And so you have to do such a thing. Now I go to the example fast. Here, an example. This is a large landslide, a large deep-seated gravitational deformation, and you can see that it is moving down 450 meters on top, 300 meters down, and then we try to put it in this scheme. And you will see that this is has a very low deformation, not so much activity in rockfall, and then we are in this type, very large, in this type of movement, because you see you have more deformation at the top than at the toe. Next one is the Eiger instability, which failed in 2006 in Switzerland, and this is blocks that were moved. This has been done by LiDAR. You see the movement were rather high, and this is about 100 meters thick. And then you see that you can have here, activity was very, the deformation was very high, rockfall also, and then the two instability, this was a first rockfall, and the global instability were on the highest, hazard. Another case is Turtle Mountain in Canada, where you have different scenario, and we can assess the frontal, the whole slope of the Turtle Mountain, the South Peak, and also as well we were able to assess just the frontal part here, which was moving faster than the rest, and with activity of rockfall. Then you can differentiate in different places. Last one is the one that has been shown by with the Ognes, which is a landslide that can trigger tsunami. And this tsunami, and this is, you have two scenarios, very fast here, slower, and then you see that in that case you have such type of deformation, and for the small area here you have a higher hazard than this one. If you go, we summarize here, and you see that clearly most of the landslide that has failed are in the red here. And some are more problematic here, the frontal crest of South Peak, maybe it will fail soon, and Kirchenstock, which is just here. So you can represent that, this is just a scheme. Here you have the present strain rate and then the state of deformation. This curve maybe, it has to be experiment, can give you some idea of the failure. It has been also assessed by the MGU in Norway. They give the similar result with their system. It has been assessed also by BGC in Canada. And I go to the conclusion, BGC in Canada, where they use here it's a lot of parameters. Here it's the density of rock slide. And so the summary is that we get the same result and very similar result, but the goal is now maybe to use them to compare them to maybe, because they are not the same base, as it's not exactly the same way to calculate, then to compare it will be a good learn. Then I skip this, because this was just what is something important, going from a rock avalanche toward a debris flow. You see, this is the rock avalanche, and you go to a debris flow there in this village. In one event, the rock avalanche creates the debris flow. 8 people were killed below this. And you see the debris flow above. I skip. This was the model. And you can see also that you can put it here, and because of the rockfall, you were in a high hazard. And the goal, the conclusion, is that if we can use such scheme to assess hazard of landslide, of large landslide, and then there is the second step I wanted to show you, but I knew that I had not so much time. It was to look at the propagation scenarios. And then the propagation scenario can be a cascade effect. It means that you have a rock avalanche, and then you have the river, and then you have debris flow, and so on. And then the idea is to identify which type of blockage or dam of the river or change in the below part, and then you give a probability to immediate hours, days, and months or years. Okay, this is the idea of doing this, is to do these two steps. So, thank you, sorry for being so long.